Welcome to lecture number 13 for ECE 376 Embedded Systems, A2D Conversion, and Analog Inputs. Now, what we've been looking at before have been push buttons. With a push button, I can get a binary input. With the analog input, I can actually read voltages between 0 volts and 5 volts. Now, the reason you have A2D converters is the real world is analog. Temperatures, pressure, flows, lights aren't just binary. They can vary continuously. In order for the microprocessor to know what's going on in the real world, I need some way to read an analog signal. That's what the A2D does. The D means digital. That's the computer world. So A2D is the input. That converts the analog world, the real world, into the digital world, the world relative to the processor. There's also a D to A output. We'll be covering that in a day or two. That converts the PIX output, digital, back to the analog world. So I can output a sine wave, square wave, vary the speed of a motor, things like that. So to start out with a couple definitions, again, A to D is real world to digital input to a microprocessor. D to A is the analog output from a microprocessor. The sampling rate inside the microprocessor, you've got a subroutine running. Every so often it measures what the input is. That's the time of the measurement. The time between samples is the sampling time. Samples per second is the sampling rate, or sampling frequency. In the microprocessor, you'll be saving these in integers. Integers only take discrete values. So if you have an analog signal, if I convert that to the microprocessor value, it'll be a fraction. Since you're using integers, I lose the fraction. So I'm going to take this analog signal and round it down. That difference between the actual signal and the sample signal is called the quantization noise. It's the difference between what you're trying to measure and what you really measured. And what you get is something like this. If I have an analog signal, say the red line, convert to a digital one, I'm going to get it at this value, then truncate to the next quantization level, and so on. Measured every sample, round to the nearest integer. To understand A to D converters, you first have to understand D to A converters. That's an integral part of an A to D. The simplest D to A converter is called an R2R ladder. It looks like this. This converts a binary signal into an analog one. And the signal is going to be 1/2 of RC3, which this is going to be 0 volts, 5 volts, TTL levels. It's going to be 2.5 volts times RC3, plus 1/4 of RC2, plus 1/8 of RC1, plus 1/16. So the net result is it'll have this binary number, that percentage of 16, that percentage of 5 volts. And to see this pattern, think superposition and Thevenin equivalence. To get RC3, assume RC2, RC1, RC0 are all 0. At this point looking down, I see 20K to ground, 20K to ground, makes 10K to ground. 10K plus 10K is 20K. At this point looking down, I've got 20K to ground, 20K to ground, 10K to ground. Plus 10K makes 20K. At this point looking down, I see 20K to ground, 20K to ground, makes 10K. So I have a 20K, 20K to ground. The output is 1/2 of RC3. Now make the output 0, 1, 0, 0. At this point, I'll have this point, think Thevenin equivalent, is going to be 1/2 of RC2, Thevenin voltage. Thevenin resistance is 10K. 10K, 10K, 20K, 10K, 10K makes 20K. This is 1/2 of the Thevenin voltage. 1/2 of a half is 1/4. And keep on going, it'll be 1/8 RC1, 1/16 RC0. So this is a way to convert a binary number to an analog one, R2R ladder. The R2R ladder is used in the A to D converter. What it does is when I start the conversion, I've got an analog signal right here. When I tell it to go, I'll start a counter. The counter then counts up. That goes to the R2R ladder that we just had. This will output an analog signal that goes from 0 to 5 volts. As soon as this voltage exceeds the signal, then goes low. That's the signal that the count, whatever it is the count corresponding to the voltage on signal. That signal going low throws a latch and saves the count, and then I can now read what the A to D converter value is. And done going low is the signal that the A to D conversion is done. What that looks like in terms of timing, I've got some analog signal right here, the red line. When I start the conversion, the counter starts counting up. As soon as the count exceeds the analog signal, that's when done goes low, that's when I throw the latch and save the value of the counter. So this is an analog converter that actually rounds up. On your PIC has a 10-bit A2D converter. What that means is there are 2 to the 10th different logic levels you can output. 2 to the 10th is 1024. So the output is going to go from 0 to 1023, 0 to 10 ones. The voltage range is 0 to 5 volts. 0 volts reads as 0, 5 volts reads as 1023, and proportional in the middle. The resolution is 4.8 millivolts per count. And that comes from 5 volts is the range, 1024 is the range, gives you 4.88 millivolts per count. And it takes time to do the conversion. For the PIC, it takes about 9 microseconds from the start of the conversion till it's done. That means the maximum sampling rate is 111 kilohertz. It's actually less than that. If you don't do anything, you can sample at 111 kilohertz. If you do something with the result, that'll slow it down. Now in terms of software, to get the analog input to work, I need 4 different registers. ADCON2, ADCON1, ADCON0 control the analog input, and the result is stored in a 16-bit register called AD result. ADCON0 controls which channel you're trying to read. I can read the input on channel 0, on RA1, on RA2, and so on. There's actually only one analog input or analog converter on the PIC chip. There's a multiplexer. Any of these pins can be connected to the A2D converter. So I first have to select which pin do I want to read, wait a couple microseconds for the voltage to settle out, then I can read the voltage that's coming to the A2D converter. ADCON1 also has AD on. What this does is that turns on the A2D converter. The reason microchip does that is it takes about 180 microamps to power up that part of the circuitry. If you're not using it, you can turn it off. On battery-operated devices, current is life. The more current I use, the quicker I wear out the battery. So if I'm not going to use the analog converter, save the 180 microamps. Turn off the A2D. In addition, there's this go done bit. When I set it, that starts the conversion. When it gets cleared, that signals the conversion is done. It's about 9 microseconds later. ADCON1 is where I determine which pin is analog, which pin is binary or digital. What we've been doing is saying ADCON1 equals 15. That's right here. That says all pins are digital. If you want to make port A analog, I would say ADCON1 equals 7. I can also mix and match and have all pins analog. That's the default. And ADCON2 controls whether the 16-bit result is, or the 16-bit register stores your 10-bit answer left justified or right justified. Left justified is used for assembler. Here's my 8-bit A2D result, and 8-bit operations are a lot easier to do in assembly. If I'm using C, I want it right justified. So this will be a 10-bit number, 0 to 1023. We're using C, so we'll use this one. The net result is to turn on the A2D converter, I need to include this section of code. So up in the main routine, when I initialize whether the ports are inputs or outputs, I will tell it that port A is input. Port A is also an analog input. Port E is input. Set up the A2D converter for right justification, oscillator for 32, stuff like that. That'll turn on the A2D. And then the subroutine to read the A2D is this one. What this one does, if I want to read, say, port A pin 3, I would do A2D read of 3. That moves 3 into ADCON1, tells it I want to read port A pin 3, RA3, for the A2D converter. It then waits 3 microseconds, gives the multiplexer time to settle out, start the conversion, wait about 9 microseconds, and as soon as go done goes low, I'm done. Return the A2D result in result. To illustrate that, here's a sample code. I'll turn on the A2D converter, then I'll just read the A2D converter and display it on row 1, column 0. And this is what it looks like. I've got the analog input. This is tied to port A pin 0. Can you see that light gets brighter and dimmer as I turn the pot? That's also tied to port A pin 0 and gives me a number. When I'm at 5 volts, the light is fully bright. That's 1023. And as I decrease the voltage, the light gets dimmer, the voltage drops. And at 0 volts, I read 0. So there's my analog input. That's one use of an analog, the A2D converter. It's a way to get a number to your processor. I can vary the number coming in from 0 to 1023. Now it's your job as the engineer. What do you do with it? Go through a couple examples of what you can do with that. First example, I'll do electronic trombone, where I can have a piano that plays different tunes, and I can change the frequency with the analog input. A NeoPixel flashlight, where I can vary the brightness of the flashlight using the pot. A stepper motor position control, kind of telerobotics, and a multimeter. Turn your pickboard into a voltmeter, ohm meter, light meter, temperature meter. Let's start with the trombone. If I read the analog input, this is a number between 0 and 1023. If I toggle port C pin 0, then wait, the amount of time that I wait sets the frequency. If I change N, I can change the frequency from being low frequency to high frequency. And that's what this code does. I want to go from 100 Hertz to 200 Hertz. So at 100 Hertz, figure out what N is. At 200 Hertz, figure out what N is. And then do a linear curve fit between the two. So this is what that looks like. On the low end, 103 Hertz. On the high end, 279 Hertz. So my curve fit's not quite right. And as I vary the voltage, I have, in theory, 1023 different frequencies I can play. So with that, I can start playing tunes. Okay, that's electronic trombone. Here's the second application. I can read the analog input. That's 0 to 1023. Divided by 4 gives me a number between 0 and 255. Have that drive the NeoPixel. If red, green, blue are all the same light levels, I get a white light. So as I vary the analog input, I'll go from 0 off up to 255 full of brightness. And this is what that looks like. So at 0, the lights are off. As I turn the analog input, this knob over here, you can barely see it. The NeoPixel started getting brighter. These are all the lights are at 4 out of 255. There's 20, 30, 60, and 255 kind of washes out the camera. Bring the voltage down. And so I have a way to set the brightness of a flashlight. I could change it so the analog input changes the color. So here, the analog input does X, that's 0 to 1000, or 0 to 255, depending upon the button I push. X gets copied into red, green, or blue. Display the value, then drive the NeoPixel. This is what that looks like. Currently, all the lights are off. As I turn the analog input, I can make the brightness higher. Nothing happens on the light yet, but if I hit this button, RB2, that sets the blue level to 111. If I now then say, let's make the green level 71, that's kind of a teal. And let's make the red level 18. Make everybody 18, I get a white light. Get rid of green. I've got kind of a pink light. Let's make blue a little bit dimmer. Let's make blue equal to 3. That's more of a pink. I can vary the colors, or the hue, by using this as my input, 0 to 255, and setting the color. Second use. Or third use. So this is what that looks like. Over here, I would have, the hand. This is, say I'm in one room. I want to open up a valve in a dangerous environment. Over here would be the robot. Whatever I do with my hand, the robot mimics it. So if I go clockwise, it follows me. Go counterclockwise, it follows me as well. And what you see on the LCD display, the top number is the desired angle, that's the reference, where it should be. Bottom angle, or bottom number, is the actual number of steps. And what it does, if I change quickly, that's the slew rate. Every pass it goes through the loop, it says if I am too low, go forward one step. If I'm too far, go backwards one step. So this is going forward one step, going backwards one step each time it goes through the loop. If I stop moving, it also stops. Another application of analog inputs. That one I think is kind of neat. Kind of showing off the area of telerobotics. Put a goniometer on each joint. As I move my hand, the robot, each joint of the robot will follow me. I could build a light sensor. Have the voltage related to light level, and as the light level goes up, the motor angle will start turning. So this would be a bright light and a dim light. Motor angle tells me light level. And finally, you can turn your pickboard into a multimeter. This is actually how multimeters are built. It's a microprocessor with an analog input. I'd like to show you how you build a voltmeter, ohmmeter, light sensor, and temperature sensor. Now start out with the voltage reading. So to turn your pickboard into a voltmeter, all I need to do is read the analog voltage and then come up with a linear curve fit. 0 is 0 volts, 1023 is 5 volts, and here I'm actually going to make it 1023 is 500, meaning 5.00 volts. So when I display it, I'll have 2 decimal places. And here's what it looks like. I've got the analog reading is 389, the voltage is 1.89 volts, it's supposed to be 1.81. If I go down, here's 1.15 volts, kind of hard to read. Maybe a little bit better. 1.16 volts, 1.11. Go all the way up to 5 volts. This is supposed to be 5 volts, and it's actually 4.75. The reason it's off is my 5-volt power supply is only giving 4.75 volts. So if I were to scale that by 4.75, I'd have the voltages dead on. But anyway, that's a voltmeter. So here's the code for reading ohmmeters. I've got 1,000 ohms, doing a little bit of algebra. The A2D reading, or the ohm, is related to the A2D reading as follows. And note that I have to make this floating point operation. Otherwise, it's going to give me some integer underflows. When you compile it, that is 5,600 lines of, or bytes, 2,800 lines of assembly. Again, a lot more assembly than I'd ever want to write. And if you look at the voltages, here's the raw A2D reading, the corresponding voltage, and the resistance. Here I've got a brown, black, red, brown, black, red. This is a 1K resistor, and here's my test resistor. It's supposed to be 1,000 ohms, and the reading is off. In fact, I can change the reading with the analog input. If you take this jumper off, that disconnects the pot, and I don't want the pot changing the reading. I also have the LEDs turned on. That draws extra current. That's going to affect the reading. Pull this jumper off. That disconnects the LEDs. They're off, so it's not as pretty. But then I don't have the current over here drawing power. So this says my 1K resistor is actually 998 ohms. And the reading is also a little bit off because I've got a 100K resistor in parallel with my resistance. So if I go into the calculations and modify the code to take out that 100K resistor, here's the 10K. Brown, black, orange. 10K resistor reads as 10K. Gray, red, red. 8.2K reads as 8.2K. I now have an ohmmeter. Change the resistor and make it a light sensor. I have a light sensor. Change the resistor, make it a thermistor. I now have a temperature sensor. Now for the temperature sensor, you need to include math.h. I'm using the function log, and math.h includes that. Here's the computation. When I compile the code, I'm now up to 7,200 bytes, 3,630 lines of assembly. Again, way more than I'd ever want to write by hand. And I've got the raw A2D reading, the voltage, the resistance, and the temperature in Celsius. So this says currently it's 980 ohms, which corresponds to 25.6 Celsius. If I warm it up, I'm sticking my hand on the thermistor. It's warming up to 30 Celsius, 31 Celsius, 32. I now have a temperature sensor. So that's some of the things you can do with analog input. I can use it as just an analog voltage to vary the frequency of a trombone. I can vary the position of a motor. I can build a multimeter, measure voltage, resistance, temperature. Then what you do with it is up to you. The program now knows light, temperature, pressure, flow, what have you, whatever your sensor is. What do you want to do with it? Totally up to you with your program. That's lecture number 13, A2D Converters for ECE 320 or ECE 376.